Morning everyone, hello to those of you who haven't met yet. So I'm coming from a psychology of hearing, a psychoacoustics background, not necessarily specifically musical. And just to retrofit Paul's question to my talk, I guess I'm making an argument for keeping the human in the listening process, and also picking up on one way in which our algorithms or the programmers of them could learn from humans. Coming to this from a slightly different background, forgive me if I mischaracterize a field, but in a lot of machine listening circumstances, not the one I'm just following, there's kind of a hugely simplified process here of capturing the sound somehow, a microphone or something pre-recorded, and passing that through an FFT to get it sort of into spectral domain, after which we can do machine learning or maybe some specific analysis, or maybe just plot a spectrogram to have a look at what's going on. So these are kind of the ways in which we make machines listen for us. Not all of the time, but quite a lot of the time, I think. Just I wanted to make a very rough comparison with human beings, sort of the parallel stages of this. We have our sound gathering device, something doing some kind of frequency analysis that is roughly like an FFT. What's a few parameters between friends, and then this information gets passed on to the human brain, where various complex algorithms happen that we understand even less than the machine listening ones up there. So there's a huge amount of sort of fun to be had comparing the brain to the algorithms, but for today I actually just wanted to focus on this sort of seemingly inconsequential first stage of FFTing things and comparing that to what goes on in our cochlea, because I think there's a few differences that could be causing downstream problems. So just to talk a bit about the cochlea, if we focus in on a bit of the cochlea, some part of the basilar membrane, we can look at how much it is displaced. So for any one little bit of the cochlea, we're getting some kind of bandpass filtered version of the sound, and moving it up and down. So for the purpose of this diagram, I've made it a sine wave. It's a sine wave that varies a little bit. And that gets turned into a signal, a voltage that across our auditory nerve, across each individual auditory nerve fibre, that looks something like that. So we get these little spikes in voltage that are very like the spikes. In fact, they're exactly like the spikes that go around our brain. This is the language that our brain speaks in. If the sound is louder, if there's more power at that particular frequency, you get more spikes. So most neuroscientific analyses count the spikes and would take this as sort of a proxy for level. Again, a few parameters to discuss, but broadly that's the case. So because we have this information at all different parts of the spectrum, if we look at different auditory nerve fibers spread along the cochlea, we can kind of reconstruct something that is very like an FFT. See previous small print. So that's one way of looking at this information that we're getting. So our cochlea is doing something a bit like an FFT. But there's also another way of looking at it, which is to do with the timing of these spikes. So if we just count how many there are, we kind of ignore the timing. But they happen at sort of specific times, so we get some information about the frequency from the fact that the spikes tend to happen at particular points of the waveform. So it tends to be just a little bit after the point of maximum displacement that the spike is more likely to occur. Not guaranteed to occur, as you can see it sort of misses some cycles. It can be a bit earlier, it can be a bit later, but approximately the time period will be the time between a lot of these spikes, approximately. For the other bigger gaps, we'll get sort of 2 time periods, maybe 3 time periods. Sometimes you can get 2 spikes within one cycle. So this is all a bit rough and ready, but there is timing information there in the spikes. So why is this interesting? One reason is that we do actually use this temporal fine structure. So if you're hearing the pitch of my voice right now, you're getting that. Some of that knowledge from the time between spikes. This is a relatively, in the last sort of 10 years, discovery that it does dominate pitch perception for complex tones. But that's just pitch. Pitch is one aspect of many. Looking more broadly, and again, this is sort of a debatable result, but maybe a debate worth having. If you look at if you get some kind of metric for how much information there is, already opening a can of worms, it seems that there's about 10 times the amount of information in this precise timing than you would find from the rate information separately. So basically there's a huge amount of information in this timing structure, this temporal structure, that we are probably using to do it. So what are we losing if we just look at the power spectrum, ignoring phase and timing information? I think one great way to answer that would be to take the output of RedFT and stick it into the brain, if there's any volunteers. Obviously we can't quite do that, but there's a few near misses which I think are informative for what we should expect of our machines if they are getting just the power spectrum out of the sound, or narrow slices of power spectrum. One that goes way back is to use a noise vocoder to get rid of this timing information. So the noise vocoder, the design of a noise vocoder is to sort of try and preserve all the fluctuations of the spectrum, all the levels, but kind of replacing it with the noisiness. It sounds like this. Okay, so it sounds quite different from speech. This is, I think that's only 6-band vocoder, so it's got a lot going against it. I think that's the women that complained was something about the women from the bingo hall. I need another listen to myself. It was the woman that complained when the old bingo hall was closed. Did anyone get that? It's easier when you know the answer. But with a bit of training, people get a lot better at, the person speaking has a kind of a bit of London twang, I think. Sort of, it's quite hard to get into from the vocoded version. But with a bit of training, people can get good at that. And Shannon, not the same information guy, noticed that with relatively few bands, we can get nearly 100%. So with 4 or more bands, we can understand most sentences, with context and all that kind of stuff. And people were aware that vocoders were intelligible before that, but his point was this is great news for cochlear implants. So cochlear implants, you'll see some of them around the street occasionally if you keep your eyes peeled. Look like they look like a hearing aid, but there's a little join, sort of a magnetic attachment to the scalp, which can pass a signal under the skin electrically. The electrical signal is then passed into the cochlea. There's an actual electrode has been inserted into the cochlea. This is only for very profoundly deaf people, so that parts of the cochlea can be different parts of the cochlea can be excited electrically, because the vibrations weren't as so this ignores most of the temporal information and relies on the spectral cues, and doesn't work for everyone. But for some cochlear implant wearers, speech intelligibility is good. You can have a conversation on a phone with somebody wearing one of these devices, so that's great news. Shannon was right that spectral information is great. Where this goes slightly awry is with when we have multiple sounds at the same time. So if we walk into a bar or a restaurant, and if we vocode that sound, then they're going to have a lot of difficulty making any sense of the different sounds that are all now mashed up together. Cochlear implant users also can understand very little speech in these scenarios, despite a lifetime of training with it. Also, if your hearing is going because of age, then we also have difficulties in these settings, and it seems that some part of the reason for that might be the reduced sensitivity we have to this precise precise timing information. It kind of gets a bit less precise, so it's as if our world is getting a bit more vocoded as we age. And I would note that this is also a major problem for all of our algorithms. I think if there's multiple simultaneous sounds, we're not very good at separating them and making sense of those multiple simultaneous sounds. So I guess I'm pointing a finger at this focus on the spectrum that we've got for various historical, and it's easier to conceptualize. So there are various reasons why we focus on the spectrum, but I'm not entirely sure it's the be all and end all. I think we're throwing away a lot of useful timing information. At this point, it could be argued that I should probably stop, but excellent. Because I can't quite stop myself, and because I have some pretty graphs, I thought it might be worth trying to communicate some of the stuff that is in the temporal, this temporal structure, to try and provide some diagrams on it, because I think that's part of a sticking point for why we wouldn't ever look at it, is we don't know what we're looking for. So I'm going to start, I spent way too much time thinking about noise. I'm going to start with a stationary noise, and it's a filtered stationary noise, and its spectrum is shown here on the left. And sort of each of these red marks here represents a point at which I'm looking at what activity we would get on a Cochlea. So effectively, I'm exactly bandpassing it with reasonably human parameters, and we get sort of at different center frequencies, we get different patterns picked out of this noise. So even for a stationary noise, we're getting sort of lots of random fluctuations, as you might expect, but they kind of look like a fluctuating sine wave up close. So we can ignore all of these fluctuations and just focus on the instantaneous frequency that is as it fluctuates here, and we can do that just by a Hilbert transform. We'll get it so we can extract frequency somehow, and look at the graphs we get from that. So this is kind of it's some of the temporal information we're getting. It's not all of it, but I've kind of tried to throw away all of the spectral information just to sort of go to the most extreme opposite. So now we have lots of squiggles on the right hand side that still don't mean very much, and I've drawn 5, but we kind of have about 3,000 non-independent ones going through our auditory nerve fibers. So here's a graph where I try and combine all of that information. I'm going to take each of the outputs from each auditory filter and plot the line. So we just get one little trace from each one, and I can keep adding in more and more and more. And I'm going to stop at about 2,000 sort of center frequencies, because we don't get much more. It doesn't change much after that. And so this, you can hopefully, well, I don't know how often it is. This was a sine sweep going through some noise. So the noise is all this sort of rapid fluctuations, and you can see the sine sweep here as reappearing as lots of nearby cochlear filters agreeing that there's something going on round about that frequency at that time. So we kind of get traces of whatever sort of harmonics we have. Here's some more noise. So essentially, from this very high dimensional temporal information, we don't have to worry about all of the separate outputs of of each auditory filter, because they tend to agree with nearby auditory filters. We can just focus on different lines that kind of overlap here. And I think this looks a lot like I've got back to the spectrogram, slightly embarrassingly. So for example, hopefully you can already read this as being some noise, but embedded in that noise are 3 harmonic components. This does, I do prefer this to a spectrogram in some ways, one of which is that we get edge tones for free. So because I'm not going to explain edge tones now in the last few minutes, but because we have any power at the edges is going to attract the attention of more auditory filters, we kind of see what looks like more power but isn't more power at the edges of sounds when there's sort of sharp cliffs in our spectrum. And I don't think that this is not the standard explanation for edge tones. I only mention edge tones to say that things like vowels, which we would consider to be a very spectral thing, if we communicate vowels by our formants, by gains, seems clearly a spectral thing, but we actually would expect the vowel filters are sharp enough that we would expect to see that in the temporal information as well. Just a fun. Going back to the original sort of noise, focusing in on 5 bands, if I take the same noise and filter it very differently, but sort of keeping a sort of fairly smooth filter, I can extract the equivalent bands and they look nearly identical. So despite quite large differences in spectrum, you can get sounds with very similar temporal structures. And I'm going to go out on a massive limb that probably can't support me by saying that, personal observation, sounds with similar temporal structures tend to sound similar. So we can take a stationary noise, filter it any way we like, and we can make it a bit brighter, we can make it a bit duller, but it still sounds like a noise. The thing that makes it not sound like a noise is that we have something in it that has a very different temporal structure, and I think the same argument can be made for harmonic complexes and filtered speech and that kind of thing. So long as the full spectrum remains audible, I think this is the thing we ought to be caring about most. Finally, my GCSE computer studies is becoming useful because I can use the phrase garbage in, garbage out, that we ought to be careful about just focusing in on the spectrum and either use a human or think a bit more carefully about what we want to get out of our algorithms.
Great, thank you, Trevor.